Hi, I'm Ethan Armas, and this is the Physics 2 Lab 6 Magnetic Molasses Lab. This lab was constructed for the purpose of observing electromagnetic properties as it pertains to magnetic flux, which is magnetic field moving through an area, Faraday's law, which describes how the change in that magnetic flux generates a voltage or an EMF around the perimeter of that area, and if there's a conducting wire, then it also generates a current within that, Ohm's law, which describes the relationship between voltage, current, and resistance, and Lenz's law, which describes how the current produced from Faraday's law generates a magnetic field which opposes the change in magnetic flux. In this experiment, we dropped a bar magnet through an aluminum tube, and we observed how it fell slower than it would when not in the tube. The system itself was the bar magnet, and the surroundings was the aluminum tube and the rest of the environment around us. The magnetic moment that we calculated from the last lab using these same bar magnets was way too high. It was 161,481.921 Tesla ampere squared. That's huge. So instead, for this experiment, for the computational model, we estimated by moving the decimal place up a bunch to be 1.61 ... Tesla ampere squares. However, using this estimation, even that proved to be a little too high, which we'll get to in a bit. The assumptions we made was that we are working in a vacuum and there are no other net magnetic fields. And you can see this table describes the average time that it took for the magnet to fall through the tube, which was 1.146 seconds. Going through this quickly, this is the Excel spreadsheet we used from the last lab in order to calculate the magnetic moment. You can see here's the math that I did in order to calculate that, mu. And you can pause here if you'd like. This is the code for the computational model portion of this experiment. So, as you can see here, this is the graph generated by our computational model of how long it took for the bar magnet to fall through the aluminum tube. It says it took about 3 seconds, which is about 3 times as long as it took during the experimental portion. This, of course, can be attributed to several factors of error in the actual experiment, but also, of course, mainly the assumption of the magnetic dipole moment that we use during this computational model. However, mu can be calculated from this experiment. Using the laws that we described here, you can relate the gravitational force that the magnet should be feeling to the magnetic force that it was experiencing and solve using Faraday's law and Lenz's law down to rewrite the equation for a magnetic field in terms of mu, and you can solve for mu there. So wrapping up, let's adjust some of these hypotheticals. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? If there were no resistivity, then there would be a stronger induced current, which would create a much stronger electromagnetic force opposing the gravitational force of the bar magnet. This could potentially prevent it from moving entirely. However, when it's not moving, there's no more magnetic flux. There's no more change in magnetic flux, which means no more induced current, which means no more force opposing it. So it would fall anyways, but the force would be much stronger, so it would fall a lot slower. Secondly, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? Holes would disrupt the current in the aluminum tube, which would create a weaker force, and as such, the magnet would fall much faster. This lab demonstrated Faraday's law and how changing magnetic flux generates EMF and an induced current, which can produce a magnetic force on the object moving through it. Sources of error between the experiment and the computational model can be accounted for by an inaccurate calculation of the magnetic dipole moment from the previous lab, as well as different assumptions that we made and other net fields within the experimental portion. Thank you.